Hey, welcome. We're back with another math hangout. This one's going to be on Calculus 1, first principles, the delta method, and derivatives. If I don't sound super enthused, it's not having to do anything with this hangout or math. It's just my back is really, really bothering today because I pulled it out the other day, and I'm just trying to get my mind off that. So I'm going to try to be a little more lively. And you should have got some coffee. But before we get started, EO here would like to make an addendum or correction to something that he said earlier. So let's just get out of the way, and so he could pay his penance to the math gods. EO, what was the mistake that you made?
During the last hangout, at the very end, when we were doing the epsilon delta proof for the quadratic limit, at one point during the inequality, I wanted the inequality to be true so badly that I ended up, well, pretending it was true. I had a nagging doubt, thanks to Ovid. I corrected it, and there is a much less elegant proof because none of those proofs can be elegant. You have to grind them out. But if you're interested, in the unlikely event that anyone listening is interested, contact me and we can talk about it all day. Thanks, Steve.
Yep, and I also had I'll pay my penance as well. I actually had a really silly math error where I tried to somehow distribute an exponent across a negative sign rather than do a binomial expansion of it. I don't know what the hell I was thinking. So yeah, somebody corrected me on that as well. So hey, you know what? We do correct each other. We all make mistakes. We're not all Landon when it comes to math. So anyways, like I said, we're gonna just jump into this. If you got questions live chat, go ahead and give us to us. And by the way, anybody can come in. I did put the link in the Great Debate Community link EIM that we have set up for it, and I did put it in the community because I'm running this hangout and I trust myself. I don't trust any of my managers not to follow the rules. No, I'm just kidding. But I'm going to just put it aside the little thing where you don't put it in the GDC. I know I'm paying attention here, and I'm not going to let anybody in that's going to do damage. And if we get sniped, whatever. But I'm going to try to pay attention for that. But let's just jump into this. So you guys are really raring to go. I can see we got Red Eye out there in the live chat going, yay, calculus. Yeah. All right, so let's share my screen here. Move this over here. Okay, so let me know if you can see this on the outside chat, guys. I can make it a little larger. I don't want to make it too large. That's probably about big enough. So let me know in the outside chat if you can see that when it comes up. There's a few minute or a few second delay here. And if you can hear me, I haven't even done a sound check. Red Eye, can you hear me out there? Wave into the audience. Hello. EO, can you check the live chat? I think Red Eye died on me.
He's in the live chat, but I don't see anyone else writing anything.
All right. Hang on. Let me just.
Okay, I can see you.
Okay. All right. Well, you can hear me though?
Yeah, I can hear you on the outside.
All right. Good enough. All right. So let's start from the derivative first principles. And we talked about the other day how we found the slope of a curve at any value for x. We actually had a very simple formula where the slope is the change of y over change of x, basically rise over run. Remember that? The change of the y2 minus y1 over change of x2 minus x1. So basically delta y over delta x. Now, using this method, this first principles, we're just going to substitute that delta x and let h represent that. Okay. So when you see the formula for the first principles formula, the limit that we're using, that's what we're going to be using, x rather than delta x. Now you can use either one. The delta x method or the delta method is just another way to represent a small change from one position to another on the curve, and I'll show you what we mean by that. How we're basically taking various lines that are secant lines, or will they be secant lines or just could they be chords lines too?
Okay, so secant lines all the way to the tangent. Yeah.
Okay, so we're taking secant lines that intersect the function at 2 points, and we're moving that one point on the function. We're keeping one fixed, and we're moving the other one, and we're taking the next tangent line and the next tangent line until it gets closer and closer to our desired point. And we'll be showing you how that's actually done. So we're going to be substituting x for delta x, and we're going to be substituting y for f of x. Again, when we ever say function of x, x is the argument to the function and y is the dependent variable. So what we say is an ordered pair is a coordinate on our Cartesian coordinate system, that x and y, that is in the form of x comma y. So x tells you how to find the x, where on the x-axis we're going, right? If we're at 0 on the x, we're basically, right there in the middle of the Cartesian where the y intersects. If we say y 0, we're literally 0, 0. We're at the origin, right? So we've all had points. I think everybody probably understands how to get a point based upon this type of notation. So I can express that point instead of saying like x equals 0, y equals 0 to be the origin. I can express it as y, comma f. Oops, you know what? That's f. Should be f of x, not f of y. Let me fix this. See, I made a mistake there. No, that's not it. Hang on.
It's like what you might want to say capital P equals x comma f of x. Otherwise, it might look like p is a function of x and f of x. But it's fine. No one's going to.
Yeah. Okay. So we're going to represent. God damn! I did the same thing? There we go. So we're going to represent the point as x comma f of x. Why did this not? What am I doing here? Why is this not showing here?
Don't worry, it's just a typo. Just put x there.
Yeah, but I don't like typos. I'm ADD. There we go. Now it's fixed. Okay.
If I made those two, you really should have put capital P equals that, not P of.
P of where?
So you see where the P is?
This one?
Capital P?
Yeah.
Yeah, I would just put equals that x comma f of x.
Well, this is how it's represented when what I was taking it from, and I'll show you the source.
That's fine.
So basically, the coordinate is represented at point P by x f of x, right? Where f of x is equal to y. So I'm just changing that. I'm substituting. So what we're going to be doing is we're going to take a small change from x, so x plus some value, and we're going to be looking at it from x plus some value and where y is represented by x plus some value, right? So as I change the value of x, I'm changing the location of the function I'm going to get a y value for, because y is obviously the dependent variable. So in the example that we're going to be using, and let me kind of show you the picture of what we're going to be doing here before we get too much further. This is this is where I taught most of this from, because I thought it was very simple. So as you can see here, right, this is what we want to do. We want to find the time rate of change. Let me see if I can make this bigger here. We want to find the time rate of change at this particular point on a specific function, any function, right? We want to find how fast instantaneously this point is changing. And the way we're going to be doing that is by going this method here. And see how they noted it here? What this is saying is, as we change the value of x, we add this h to it, which is the x, part of the x component, right? We are going to have to go up a little bit here, which we're going to call g. And this point that represents the change of x plus the function of x plus h will be represented here. Now, this line that's produced here between these 2 points has a particular slope. This slope is an approximation to this line that we want, because we want the tangent line to the point P, which is the instantaneous velocity at that point of the function. By getting this point here, Q, or moving closer and closer to this point, what's going to happen? This line here is going to start getting more vertical. It's going to change the slope. It's going to more approximate the slope we're looking for. That's what the delta x method is, or first principles. It is using that type of formula to approximate closer and closer and closer by taking a limit as h approaches 0, which is going to be pretty much the point. But as h approaches 0, this line here is going to more approximate this line here. And I actually showed it this way too, and I thought this was a little more easier to maybe just kind of see it this way.
Yeah, it is easier to see that way. So you can draw a secant between 0 and 1, Steve, and then.
So what I did was
broadcast somebody at
oh shit. Okay, one sec. Let me give you guys mods, because I can't do 3 things at once. Hey, we got Justin in here.
Haven't seen him in a while.
Yeah. Oh, I don't want to present him. I want to show him. One sec.
Just pass me mods. I'll present.
Yeah, I got you. Mods going out. Mods going out. Hey, Justin, you get mods too. Whatever. You want to learn about math? Go for it, man.
No, it's not my subject.
Well, we get to learn here, so
I don't want to
Cheers
learn.
to you.
I don't want to learn it.
You want to learn? Come on, man. This is educational stuff.
No, it is, but this is, yeah.
Take one for the team, buddy. Come on. Just sit in here. So I can say that I had, you know, some younger creationists actually come in and want to learn math for a change.
It has nothing to do with create.
Well, yeah, well, you're right. It really doesn't. Math is math, right? So
No,
your choice. Okay, whatever, man.
I'm just super right brain, and you know, my logic on this doesn't work on the math side.
Well, you know, we're offering here, man. So
okay,
you want to give it a shot? You want to try? Because if we can explain it to you, then it's like, hey, we felt. I'm preacher to the choir when it comes to like challenges to EO. EO teaches this stuff. He's, you know, got it down to an art form. He's exceptionally good at it. So I'm just going through the motions. By the way, I should note to everybody, I'm not a mathematician. I'm completely a lay person. I'm going back years on this, but I enjoy this kind of stuff somewhat, and I enjoy talking about it. So that's the only reason why I give these things. These little presentations. If you like them, great. If you don't watch.
So Steve, can I give a big picture view and we can incorporate Justin here? So why Steve is doing this is the following. Everybody knows how to find the slope of a straight line. It's simply rise over run, and they have constant slopes. For example, y equals 3x plus 2. The slope is just 3. Now, one of the reasons calculus was invented was how do we find the slope of the curve at a particular point? Now, what Steve is doing, he's going to draw successive secant lines that it touches the point, and the Latin for touch is tangere, and so we're going to find the slope of the tangent line. So Justin, what we're going to do is you pick any point you want, Justin. Oh, what did you say? 1, 1? Is that the point you chose?
Let's start. Yeah, let's start with the base. I picked 0.11. I actually started with 4.2, but I thought I actually redid it. And I did it as 1.1 because it's a little bit easier to see, I think. And by the way, Red Eye says thanks for the visuals. They really help. I think so too, Red Eye. I like visuals. I think visuals make a huge amount of difference. So let me show you what we're doing on this function. This is a simple x squared. This is a parabola. This is one of the most basic, about the basic quadratic you're going to get, because it's just x squared. The vertex is at the origin. It's not inverted or twisted, or, you know, it's just a normal freaking parabola. So I want to know, what is the time rate of change? How fast is this function changing at this particular point, 1, 1? Now I could take a line, okay, and I just took a line and I just put it straight through a bisecting, well, not really bisecting, but it's a secant here. And I just picked 4 points on that line to kind of gauge the line, and said, okay, at this point, I'm approximating the function that I want, or excuse me, the tangential line I want, which is going to be the one right at that point. Now, obviously, this was nowhere near what we're looking for, right? It's a really bad approximation. This actually, anybody know what the slope of this is? I do, but it's not you, EO. But what do you?
I can't see it, Steve.
You can't see it?
Can you, Drake?
Yeah, I can see it's a straight line. Doesn't have any slope.
It's a horizontal line. So what's the slope of a horizontal? What's the slope of any horizontal line? Think about it.
1.
No.
Or is it 0?
0.
So I thought it was up. If I have it up and down, it's 0. If it's
no, it's up and down. It's undefined.
It's undefined. Oh, that's what it was. I'm sorry. Yeah, there you go.
So if it's straightly vertical, if it's orthogonal to the x-axis, meaning perpendicular, it's undefined. So this is just a slope of 0. That doesn't tell us anything, right? So we go to another approximation. What I did was I slid this point down from negative 1 point, which is right here, and I move it down to the origin, 0, 0. Now I have another tangential line. This tangential line is a little bit closer to what we're looking for, right? You can actually see that it's getting closer to what we're looking for. By the way, this is the line we're looking for. Let me make this a black color. Maybe it'll help see. Can you see it now, EO? Oops. No. Can you see that, EO?
But you slipped. You meant to say another secant line.
You can't see the tangential line?
No, I can see. It's fine. It's beautiful.
Okay.
Awesome. Tangent. You meant another secant line.
Yeah, I added another secant line here to approximate the tangent line that I'm looking for. So this slope right here, I calculated. I think it's a slope of 2. And then again, we're actually looking for this particular one, and I'm giving away the formula for this line. Don't worry about that. But this is actually the formula, and I'll show you guys how to get this formula when we're done or near the end. But this is the actual line, the tangential line we're looking for at point P here. And again, if you think of these points right here and right here, this is Q. It's getting closer and closer, and as Q gets closer to this point here, my approximation is getting closer and closer. That's the gist of basically what we're trying to do here. Okay, using first principles. So let me move this out of the way because I already showed you this. Okay, so we're going to actually do the derivative of x squared based upon first principles. Now we all know by now the derivative of x squared is 2x. I think basically everybody and their brother doesn't even know calc knows that. They may not know why, but they do understand that the derivative of x squared is 2x. Now we can apply the power rule to that, obviously. We all pretty much know the power rule by now too, right? Anybody remember? Oh. Anybody
remember?
Okay, the power rule is we subtract 1 from the exponent. We move the coefficient, we move the exponent to the coefficient, subtract 1 from the exponent. So x squared, we move the exponent down to the coefficient, right? So it's 2x, and then subtract 1 from 2, leaving 1, which is just x. So the derivative of x squared is 2x. That's using the power rule. And we will get into explaining why that is using the power rule using EO's notes, because I was not going to type all this stuff in. It's just not the way I'm feeling right now. So we're going to cheat and just show you a picture about why that proof works. But let's actually find out using first principle why that power rule works for this. Why it actually x squared, why the derivative is actually 2x. So if I excuse me, oh, this was for the I wanted to show you real quick the other line that I had, that other secant line. There was a slope too right here, but I don't think we can ignore that. So let's just kind of skip past that. I don't know why I concluded that. But what we're doing again, since the slope is delta y over delta x, and as you saw, as q, that one point, moves closer to p, that line that pq forms, right, approximates the tangent at p. Okay, so that ASPQ should have a line over here on top of it. It would really kind of be correct. So EO, I'm aware of that. I wasn't sure how to put a bar over that, or vinculum. But as Q approaches P and H approaches 0, we have a tangent line at point P where Q equals P. All this is saying is, you think about it, as that point Q approaches P, the point we're looking for, right, as the H, right, which is the delta X, if you remember, goes to 0, we now have the tangent line at P that we're looking for when Q is equal to P. Is everybody kind of getting that so far? So the closer we're moving Q to P, the closer we get to the approximation to the actual tangent line we're looking for. Sound good? Okay. So we all know the slope formula, right? y2 minus y1 over x squared minus x1, which is the same thing as saying delta y over delta x. And we're just going to change those variable names, or as Ronnie likes to say, veritables. Right? He likes to say veritables. G over h. So we're going to call delta x h and delta y g. Now again, if you look at the thing that I showed you first, is all we're having is a change of x, which is on the x-axis, right? So it's a change of x, which is h, and a change of the y-axis, which is g. And remember, g is a change of the y-axis. From here, this line here, to up here is changing on the y. So this is the g. So all I'm doing is saying g is equal to the delta y, h is equal to the delta x. Okay, so dun, dun, dun. Since we know g is equal to the delta y, we can also say that g is equal to y2 minus y1, and y2 we can set to f, the function of x plus h, and y1 being f of x. Now, this is where people start kind of losing their mind. And I think EO could probably agree. When they first start learning about this stuff, they're going, what does this mean? But it's really not complicated. It's not. All this is saying is that since y is normally the f of x, we all agree with that, right? Y is the dependent variable of the independent variable x. I'm just setting that to be y1. But my y2, my second position, is just f of x plus that h that I added to x, right? So now I have y2 minus y1, but y2 is f of x plus that h difference minus my initial y1, which is f of x, which is just y. Totally makes sense there, Drag?
Shit, I was muted. Yeah.
Okay.
So then we got the slope formula. Let's see. Since
I don't know who else is in here, so I'm not sure else to like ping on. to ask. Let me see if I can get the window back up. There we go. Oh, it's just you two. So come on, guys. You want to join in? I want to ask you guys questions. So come on, Kelso. The link is, you know, the GDC.
Yeah,
so
let
me walk you through this again, because I don't want you to be confused here, because this is critical. If you don't get this, nothing's going to make sense after this. I am just substituting what we know into other things. I am just saying, look at y of 2 minus y of 1. You totally agree that's a change of y, right? Delta y. We're just going to call that g. And since g is the change of y, the second position, the second y, is equal to just f of x, which is our normal y, plus h. I'm just adding h to that x. That's it. If that's the case, then g is actually equal to f x minus h minus f of x. Okay, that gives you g over h equals f h plus x minus f of x over h. Now, when you combine all this and you say, okay, if I let h go to 0 as approaches 0 and q, that point q approaches p, then g of h, which is just my slope, right, will at point p is what I'm looking for. So the derivative, remember this notation, right?
dy over dx.
Leibniz notation equals the limit as h approaches 0 of f plus h plus x minus f of x over h. And again, this is just putting these two things together. It's just saying f of x is my normal y, y1. Think of this f of x here, right? Like, you guys can't see my pointer, can you?
Yeah, I can see it.
Okay, so as f of x here, this is my y1. That's all I'm doing. I'm just putting y1 here, and y2 is f of x plus h. So it's y plus that h, or excuse me, that x plus that h value. That's it. But people get confused as they see this and they think, wait a minute, if h goes to 0, I'm going to be dividing by 0 here. That's not what's happening. Okay, that's not how you actually evaluate this. You can't. You remember we that's why I had the limit thing first, right? You can't divide by 0. So that'll actually factor out as we go on. So don't let that throw you. Don't go, oh, I don't understand this because h goes to 0. If h is 0, it's undefined. No, because that h will actually be factored out as we've done before in order to simplify limits where we can actually take the limit with not having that blow up and the universe be destroyed.
So, if I may, Steve, a couple of things.
Yeah, is that good so far, you?
You're fine. Just a little typographical stuff. You could move that subtraction smoothly. A couple points. Steve did well to highlight, and this is what's called the definition of the derivative, what Steve wrote there in blue ink. And it's really important because what we mean by first principles is find the derivative using the definition. Now, we'll learn all these powerful tools later, and Steve has highlighted some of these with the Taylor series. But this is, again, foundations. This is the definition of the derivative. And I want to point out, it's not at all clear that the derivative always exists for every function, but we'll save that for a rainy podcast day. Sorry, go ahead.
So, but so far so good.
You're doing great, Steve.
All right. Yeah, the reason I highlighted this in blue, whenever you see blue, I'm kind of using definitions or something that's very critical. This right here is the definition of a derivative. Okay, so this is important because this is the foundation of all calculus using derivatives, basically. So we're going to kind of utilize this formula, but I want to make sure everybody gets this down. I mean, because it looks kind of complicated, but Drag, do you see what we're doing here? We're just taking y2 minus y1, and then moving, approaching that tangent line at P as h goes to 0. That's all this is really saying.
Oh, Steve, you might want to hit, for those in the chat, it's hard the first time you see this. Maybe really highlight that x plus h minus x results. They might be wondering why aren't there two terms in the denominator? Because the x is canceled. Maybe hit that if you didn't already.
Where are we talking about?
So you did a great job putting it as y2 minus y1 or x2 minus x1. So maybe
okay. It should be, I got you. Okay, yeah, because
you're fine. I'm just saying in case anyone needs clarification.
Okay, let's see here. Okay, so the differentiation from the first principle, which is the delta method, right? That's what when you hear delta method, it is the instantaneous rate of change with x with y with respect to x. This is the whole shebang right here, because whenever you take calculus, you can see it written any of these different ways. They mean the exact same thing, and this EO is why I hate math, because there's so many different ways of representing something that means the exact same thing, right? But let's look what this is saying. This is what the first part is actually what we just already discovered is our derivative definition. It is actually taking the limit as h approaches 0 from the point Q as approaches point P. This can also be represented by delta x, right? Because we initially said way up here, if you remember, that h equals delta x, right? So this is why we have h on the bottom here. Delta y is g, delta x is h. So we can actually represent the same exact thing as h by sticking in delta. Thus the delta method. But it's more symbology, right? It's more the right two things here than one h. And this is actually a capital delta, right? You might also see it in lowercase. And a lowercase delta is this little symbol here. So you might see it written this way. Don't worry. These all mean the exact same thing. Okay, but whatever course you take, you might have it written differently. Don't freak out. So you can have h, delta x, capital, or delta x lowercase. And maybe EO might know the history of why they use one or the other that you might want to go into. I have no idea, to be honest with you.
Oh,
except to confuse poor calculus students, because I think math teachers like to do
the capital delta, the delta versus You know what's funny? This is fascinating. Did you know that the partial derivative sign is sometimes called atled, which is the opposite of delta? I'll just point out, Steve, this is your area. They use delta all the time in physics, right? Delta V. You know what is it? Lift per.
Yeah.
How much energy it takes? Go ahead, take off with that.
Yeah. Well, delta for like rockets. You're talking about the instantaneous change of velocity.
No, yeah, I'm talking about the fuel, how much energy it takes per kilogram.
Yeah, well, if I remember correctly, as you go, I don't know anything about rocket science. I'm not. I mean, Reg is the guy for that. But I remember rockets, as they go up, they actually get more efficient because they have less fuel. They're less heavier, so they get more efficient. But your change of velocity has to be proportional to what your trajectory you're trying to go to put in orbital. Your orbit, but I don't remember the formulas for any of that. No, that's all kinematics, dude.
I'll just point out, physicists love deltas and mathematicians prefer the h's. But go ahead, Steve.
Yeah, that's a good point. Okay, that's a fair enough point. Yeah, that's true. When you're talking about physics, you do usually more use delta. For example, like acceleration, right? There's no such thing as decelerate in physics. You never decelerate. You have negative acceleration, and when you're taking the difference between acceleration between two time periods, that's the delta. Right, you're taking a delta of the acceleration. You don't look at it from h. You look at it from delta a, right? So you got a good point there. But I don't know why they use capital and not capital. And I didn't know the name of the partial differential symbol. And by the way, I could never write that symbol properly. It always looks more like the symbol for sigma for statistics. I can't ever get that symbol right. It's like an at symbol, only like weirder. What's it called?
Right. It's just the partial. We just call it the partial, but it kind of looks like a delta the opposite way. The lowercase delta.
Yeah, similar. It's similar.
Drake, is it me or does Steve time out sometimes? Can you hear him consistently? Drake? Is Drake there?
He already fell asleep.
Oh, sorry. Keep muting myself.
Am I cutting out to the live chat?
Steve's off.
We're earlier. Okay, no, that is. Okay, I hear you now.
Okay, well, let me know if I cut out. I seem to be fine on my end.
Okay, let's dive in.
Okay, so again, this is everything on blue. Memorize, because that's critical. You have to know that.
Yeah, that notation that we ended up producing, the dy over dx equals limit of as h goes to 0. F of x plus h minus f of h over 8. F of x minus over 8. Ugh. That's what I'm familiar with, and that's what we
right here. The first one.
Yeah, that first one.
Yeah, that's common, but in higher maths, they kind of like make things difficult, so they use this stuff. Whatever. I'm just giving EO shit because I hate higher maths. But anyways, so let's actually do this. So, oh, by the way, I'm not even lying. I am actually thrilled that I actually remember this stuff. I for the longest time never bothered with ever really getting back into this stuff, and the fact that I can actually remember it and be able to at least explain it, I'm cool with that. I think it's pretty cool. I'm actually entertaining myself, so I want to throw that out there because I don't give myself props enough. But I actually kind of do know this stuff, so whatever. It's cool, right? Again, if Ronnie wants to come in and explain any of this stuff, he's more than welcome to.
Oh God, no.
Just saying. I mean, just throwing it out there. We'll so
Why did we lose Justin? What happened?
He didn't like the content.
I'm telling you, I've noticed something with certain people. They don't want to learn. So even if I had no idea what's going on, I'd probably sit and go, okay, I'd try to take a listen. But
yeah, I've sat in Christian hangouts and just listened to them talk about not the Trinity, but the diune or whatever
triune, the triune and diune natures. There actually is a diune, if I remember correctly.
Yeah, I've sat in for like an hour and a half and just listened to it, just because I didn't agree with any shit they were saying, but I sat and listened to it because I thought it was interesting. You know.
Oh, we should get Edgar to explain this, Drag.
No. If he's in the chat, I want him to explain this. That would be entertaining. I legitimately would like to see him explain this shit.
Steve, I wanted Justin to stay because I would have been so polite until the very end. And I would have said, at what point did we consult our worldview when doing these calculations?
There we go. Yeah, exactly. What worldview changes our calculations? It's funny that you say that, because I wanted Justin to stay, because if we can explain to him, we can explain to anybody. And that's one of the critical things of any instructor, right? We've all done instructions. You've done tutoring. I've done tutoring and training. One thing that you gauged upon, did the person understand what you were saying?
Yep.
So hey, by the way, Kenny Rhodes live chat, dude, I got to get with you later on. Loved your stuff last night.
Pastor Dr. Mr. Kenny Rhodes, PhD.
We're going to get with you later, my friend. That was just, you were superb. I give you kudos. I just told you that what you're getting yourself in for. But he says, do you have a Zeta method for us non-math heads? No, I do not. But maybe EO might.
You're going to have to struggle through it, Dr. Mr. Kenny, Pastor Dr. PhD Rhodes. Sorry.
And by the way, he went to a school that's actually accredited, so he does have a full PhD. He's legit.
Do you want to clarify that, Steve? Because that came up earlier. Maybe just clarify that for the audience.
What?
That he went to an accredited school.
Yeah, his school is accredited. He did not go to like Ken Hoven's Bible college or got a mail order PhD.
Up the trailer in the middle of Arizona.
Yeah, his legit study. I mean, he is a adjunct scholar to Reasons to Believe. They don't just accept people like Ken Hovind or something like that. So, and I've actually looked at some of his stuff. I mean, yeah, he knows what the hell he's talking about, way more than I'll ever get into. But I just found it really entertaining that he was just pointing out to G-Man, he didn't understand the concepts of heresy or orthodoxy or heterodoxy. And this is a guy that's supposed to be preaching to people. And I know we're really off topic, but hey, welcome to the Great Debate Community.
Oh,
this
actually,
is what we do.
I should put the link in the chat for Kenny, where he was preaching about adultery. Go ahead and I'll put that in the chat. And so, Kenny, I want you to see something that G-Man was putting out there 3 years ago. And you can.
He did correct that, though, didn't he?
He did, but it took him weeks. It took him literally weeks to get that corrected. Because in the meantime, he called every other person who talked to him a heretic. He called every other person an apostate, and that's where I remembered this from, because he's done this before.
Well, tell Kenny what he was teaching.
Oh no!
We're off topic because
I want Kenny to watch it for himself. I'm gonna put a link. Hold on, let me find it. But go ahead, Steve, with this.
That's a great thing about the Great Debate Community. We incorporate a lot of stuff, right? I mean, just I love tangents. Okay, so let's go back on topic here. Kenny, you're welcome to join and learn some math too. Even though you're way ahead of us, probably. I'm sure you had all this stuff. Kenny's had logic, so he knows.
So you love tangents, Steve? What a segue.
What a segue. Yeah, exactly. What a segue. Tangents. I get it. Now, we're going to find the derivative of f of x using these first principles. Now, when we do this, you'll see why we just like the power rule, because it's so much easier, obviously, because this is a pain in the ass. So we're going to start with the function f of x. Okay, no big deal. Do I need to make this any bigger? I think so. Let me just. Okay. The link to get in is in the GDC if you want to come in, Kenny. So starting with this, f of x equals x squared. Now, that is y1, correct? y2, we need to find out. Y of 2 would be f of x plus h, which is basically what we do is we take x of h and stick it in where x is, okay? So now I have a equation here of x plus h squared, because I'm just taking x and adding h to it, right? So you just you take x plus h and you stick it in the variable. Done. I'm not going to do the expansion here because we've already done this before, but we know when we take a binomial expansion of x plus h squared, we're going to end up with x squared plus 2xh plus h squared. I think everybody understands that, right? By now, we've already been over that. Yeah. Okay. because I mean, I'll do the binomial expansion, but it's basically, you know, it's x times x, then you have x times h, and then h times x, and h times h. So this is what we end up with. So going back to our original thing of our derivative definition, right? The dy dx is equals to the limit of h goes to 0 of this formula. I'm just sticking in stuff now. That's all I'm doing. So remember, I'm basically saying y2 minus y1. Keep that in your head, and it'll save you a lot of heartache. It is y2 minus y1. That's what I'm doing. So here's the formula for y2, and here's the formula for y1. It's basically my functions, right? So I'm taking the point that this comes up with minus the point that this comes up with for y, right? Because y is equal to x squared. So whatever value I have for x, I get a y out of it, right? This is what I'm saying. I'm just saying y2 minus y1. Okay. Now, what happens when you put these together? What happens to the x squares here? And I put the brackets in for a reason. The reason I added these is because I think this way it shows the way to group them, that this is y2 minus y1. You can remove these brackets, okay? You won't even see them in probably when you're doing this in actual class, but this is how I like to group things, because I think it's more visually appealing that I'm seeing now that is y2 minus y1. So what happens here to the x squares? Anybody?
Drag, what happens to x squareds?
It looks like they cancel out because you have a negative.
They cancel out.
Yeah, negative x squared and regular x squared.
They cancel out. So I am left with, and by the way, I think, and I don't know the reason for this besides just standard practice, but generally you always start with the highest exponents and work your way down. Okay?
That's what I was taught.
Yeah. Okay. So we're gonna rearrange this formula, and basically you cancel out x squared. And again, if I had a middle pen, I'd just go cross and put a little x and arrow. What is the little line with an arrow going through it is how I do it. So I'm going to rearrange it. I put the x squared on this side to the left, and I'm going to end up with the limit of h approaches 0, x squared plus 2xh over h. Now we learned, if you remember, I can't take the limit by just sticking 0 in there, because what happens?
Everything goes to 0, and then you're going to get something that's undefined.
And the universe blows up, and we don't like the universe to blow up. That's bad. So what we do is we just simplify this, and I actually broke this down more so than what I would normally done, just because I want to show you, but and I even prove it to you why this is. But what we do is we break it down like this. I can actually just say that h squared. I actually put it in Wolfram here to show you, because some people have a hard time looking at this. But these terms could actually be rewritten with just h squared over x, or excuse me, h squared over h plus 2xh over h. Right? I'm just taking the denominator and I'm separating the terms. Remember, in algebra, terms are separated by pluses and minuses, and I'm just separating these two terms, h squared plus 2xh, and I'm just showing them individually. They're equal to each other. How does this evaluate? Evaluates as true, right?
It's all the same base. Yeah.
It's the same base. Exactly. Bingo. You've got it. Same base. That's all I'm doing here. So,
I would have looked at that and I would have tried to divide everything by that.
This is where,
sorry,
yeah,
folks. Precision
exactly,
language is
Drag.
important here. Oh, sorry, same denominator. Base refers to exponents. Sorry, guys.
Base.
Okay,
Oh yeah. I'm sorry. Yes, right. Same denominator. Fuck.
Same denominator base. How about that?
No, it's the same denominator, and that is something that needs to be highlighted. When I look at that and I go, okay, I want to simplify that, and I see everything up top has been multiplied at some point by an h. So I know that since my denominator is an h, I can take an h out of everything up there. So the h squared, I can take an h from that, and the 2xh, I can take an h from there. So I'll be left with h plus 2x if I take that h away. Okay,
let's find out. And you're exactly right on here. This point right here is where most people have a lot of confusion. They're like, oh, what do I do to get rid of this h on the bottom, right? Because I can't take the limit as it goes to 0 if my denominator is undefined. Well, do exactly what we did here, right? And you're right. We cancel these out, right? Wait, you know what? I made a mistake here. Is that right?
Because it'll be, you'll have it. H,
yeah,
it'll just be H.
Yeah, see, but see,
it'll just be
I got my own mistake, right? Because I was like, wait a minute, that's not right. So,
and then you plug in the H thing. You make H go to 0, and then all you'll be left with is a 2x.
Exactly. So here I have h squared with H in the denominator. You just subtract 1 from the top, right? You're just left with H. right? And again, this works with any exponent. If I have x cubed and I divide it by h, I have x squared, right? I'm just subtracting 1h from top and bottom, exactly. So same thing here. I'm just subtracting 1h from top and bottom. They cancel out. I'm left with 2x. So exactly right, Drag. What happens when I can take the derivative? And this is why exactly why I did limits first, though, right? Does it make sense why I wanted to go over limits before we went over anything else? Because this probably wouldn't have made sense a couple weeks ago before we went over limits, right?
Yeah.
It just wouldn't have, because you would have been like, well, how do I take the limit of this? So now, as you're right, you take the limit of h goes to 0. This goes away here. What am I left with? The derivative of x squared equals 2x. Yay. Okay. Everybody got that? We good on the live chat? Isn't that awesome? You guys are not impressed by this. Okay, whatever. Enthusiasm. EO's impressed because he's a math dude. All right, so let's try a different one. Drag.
Oh, Steve, great job. But can we scroll up for a second?
Yeah.
An important point that students, and what you did is great. I would have just factored out the h, but what you did is fine. I want to point out, if you can scroll up one more level. One more? There we go. Do you see where it says the limit is h goes to 0 of h squared plus 2xh divided by h? Can everyone see that? Unfortunately, many students whose background is a little bit weak will pretend they can just cancel out the h and be left with h plus 2x. So these are one of the terms. You have to have a strong grasp of factoring, or do what Steve did and rewrite them over a common denominator. So
yeah, you can't cancel out top and bottom across a negative sign or plus sign. You've got to separate them out like I did.
Or factor it out, but yeah.
Or factor it out, right. And by the way, this is just the way I did it. This is just one way to do it. You might actually have to write it out each and every time. I just figured out the thing for f of x and f of h of x this way, right, and then stuck it in. But there are other ways you could conceivably work it out. But I think this shows it the easiest. But let's try it using a little more complicated formula, right? Now, excuse me. Now, Drag, I know you could probably by now look at this formula and equation and say, yeah, I know the derivative. I can do it in my head.
I can use the power rule. Yeah.
Use the power rule. So,
that's really
so you already know the answer ahead of time, which we'd expect to get, right?
Yeah.
Okay. So let's see if we can do it using the first principles, though. Okay. So I'm setting f of x, right, with 2x squared plus 3x. I'm finding out f of x plus h, and all I'm doing now again, right, is I'm taking x plus h and I'm sticking it where x is. So I'm, instead of having 2x squared, I have 2h plus x squared, and I stick it in here, right? So let me just cover this up so we go step by step here. Do you see how I get to this formula here?
Hold on, let me look at it for just a second.
I'm just taking x of h, right? I'm just putting it where an x is. And I'm putting, it's a quantity, right? So if I have 2x.
And Steve, go
ahead.
Let me give you a plug. If anyone's confused at this point, please check out Steve's video on order of operations, because that's going to play a key role here in a second.
Another reason is why I did a video on order of operations. Order of operations is critical, which, by the way, I messed up the other day on one equation because I didn't pay attention to the order of operations. So it is critical. You know these things. So do you understand how I got this particular equation, though? I'm just putting h plus x into where x is.
Yep.
Okay, so this quantity, think of this quantity as x. I'm saying x equals x plus h. And I'm just sticking it in there because I'm just adding h to the x.
See, if I may, when I teach my students pre-calculus, one of the things I teach them about functional evaluation, Dreg, if you could imagine a picture of a red cherry. So we have x equals 2x squared plus 3x, right? So imagine now a red cherry. If I say f of red cherry, that means that wherever I see x on the right-hand side, I have to put a red cherry. No matter what it is, the rule is f of x equals 2x squared plus 3x. So if I change the argument, what's inside the parentheses, then I have to change it on the right-hand side too. Sorry, Steve, go ahead.
Okay, so this is where it starts getting fun. Binomial expansion of the x plus h, right? We actually have to do the exponent first. Would you agree? We can't distribute the 2 until we take the exponent, because what has a higher order of operations?
At the x, well, there's parentheses, then exponents.
Okay, but there's nothing to do in the parentheses, right? I can't simplify.
Yeah, you can't do anything in there. Yeah, right, so next you go to exponent.
Okay, so when I take the expansion, I end up with this. This time I actually showed xh plus xh just because I wanted to show you the entire expansion. But what happens when you combine those, right? You get 2xh, right? So I'm actually going to just rewrite that real quick.
2xh. Where'd you get 4? Oh, okay. I was like, where'd you get 4? And I know I see you multiplied everything out. Foiled.
Yeah, FOIL. Okay, so first, outer, inner, last. So I'm just going to combine those terms. So the binomial expansion for this, I'm just ending up with x squared plus 2xh plus xh squared. And here, there's nothing to do with it, right? I'm not distributing it yet. I will, but I just wanted to get that exponent out of the way just to show you guys. Okay, because I like when I was doing things, I like to do things step by step, and the reason I do that is because I get lost really easy. Right? Even in nuke school, if I didn't do things step by step, I got lost. I wanted to make sure each step I knew what was going on, so I can go back and find an error if I needed to. Right?
Yeah.
Okay. So next step. Now I'm going to distribute, and this is a simple distribution. This is called distribution of multiplication over addition. Okay. And so I'm just basically 2x squared, 2 times 2xh. And I'm just doing the same thing over here. 3 times x plus 3 times h. So I'm ending up with this big old long formula now. We good to go on that? So this is now equal to this.
Stevie, let's hit the fact that you distributed the 3 across the x plus h. Students often forget that. So it's 3x plus 3h as you've written.
Yeah. Okay. So now we can put it in here. Now, when we set this up here, Drag, what do you think the fx plus h minus f of x is going to look like? The y2 minus y1. What do you think it's going to look like? It's going to look like this entire formula here minus this, right?
Mm-hmm.
Okay, that's exactly what it is. This entire formula here, I'm sticking in here for this fx plus h, because that's what it is, and f of x, which is this. So I'm just putting this entire thing into here, and I'm just substituting f of x, what we already know the f of x. It's this formula here. So I end up with this big old long formula. Okay? We good to go?
On. I'm looking at it.
It's kind of hard sometimes when you go, okay, I'm looking at this, but it's really simple. All I'm doing is I'm just figuring out what this is, fx plus h, based upon what I know, f of x, and I'm just using our derivative formula, and I'm just sticking in what we've calculated this to be, right? We figured this out to be, and I'm just putting it in this derivative, the definition of derivative. I'm just sticking this whole thing in right here.
Mm-hmm.
Okay, and I end up with this. So my original formula that was like right here is this, and I end up with this big old long formula minus the original formula, which is f of x, or 2x squared plus 3x. So I'm getting all these different terms in here.
Okay.
Is that making sense?
Yeah, I just need time to look over it.
Yeah, well,
make sure that I understood it.
Yeah, think about it this way, right? Look, see the f of x up here where my pointer's at? I don't know why I'm actually pointing at the fucking screen with my finger, like you can see that.
Yeah, no, I see your pointer.
No,
Yeah,
I'm actually literally, I'm pointing with my finger as if you can see my finger.
Why are you doing that? Because
I'm a fucking idiot. What do you want? Okay, so by the way, we curse in the GDC. Sorry, kids, if you ever watch this. This is for teenagers. So f of x, right? If you look,
that's going to be the original problem. Yeah, for f of x, that's easy enough.
This is right here, and so the same thing. X plus h. This is the original. You know, we're just sticking in x plus h for x, and then we're factoring it all out. We get all this again. Y2 minus y1.
Okay, and we've already figured out what that is from the previous problem above. Okay, yeah.
And that's why I did that way. Instead of having to write everything over and over and over again, I think this to me is a very easy way of doing it. That way you kind of figure out the stuff beforehand, then you can stick it in the derivative, the first principle derivative definition. So now we just do cancellations, right? X squared cancels with x squared, right? We got a 3x cancels with a 3x over here, and we left with this 4xh plus 2h squared plus 3h. Now again, I'm just going to rearrange this because we always put the exponent to the left-hand side, right? The highest exponent down. So I only left it this way because I want to show you. We're just canceling out this first term. We're just canceling out this term, and we're canceling out this term. And this term. So basically, we were left with 4hx. We're left with 2xh squared, and we're left with this 3h over here. And I'm just rearranging them. That's all I've done. But now we run into a problem again. We can't take the h goes to 0 because the universe blows up. We don't want that. So we have to figure out a way to simplify this, right? And I just did the same thing as I did before. I just split up the terms, factor them with a common denominator, right? And now I can actually simplify this. I can just say, okay, well, 2h squared divided by h is just 2h, right? I'm just reducing it by 1. I can cancel out the h's here. I'm left with 4x. I can cancel out the h's here. I'm left with 3. And now, Drag, what happens when I take the h goes to 0? What goes away?
Oh, looks like all those h's went away. Except, actually, hold on, wait. That. Okay, if you take h goes to 0 now, then that 2h goes away.
This 2h goes away, and what am I left with?
4x plus 3. Yep, that's what I have on the side.
And what did you say the derivative was using the power rule?
4x plus 3. I put it in the side chat earlier.
It works. Okay. Now, let me ask you before we get into the power rule stuff. I got to do the point slope formula. I'm going to show you how to get that in a second here. But before we go further, which would you think would be easier to use if you come across this equation here, 2x squared plus 3x? What do you think is easier to use? The power rule to go through each step that I just did right now?
Power rule. That's why people do it. Like, oh god, that's what I hate is trying to do that stupid formula again when I can do the power rules, and it takes.
But they want you to learn the basics, right?
Yeah,
they want you to learn where that power rule comes from. Drag.
You both are from the military, right? So think of first principles as basic training. You have to pass basic training.
That's right.
But afterwards, at least you know why the power rule works. But people, you have to build upon principles, right? If you just say, look, use the power rule, you're never going to understand why the power rule works, and that's going to be a deficit in your learning. And that's what I think I see happening with a lot of people in the community is they jump so far ahead, they mix out on the basics, and they don't know why things are the way they are. Don't we see that a lot with the Clown Car Posse?
Oh yeah, they'll fix something that they think is special and go, oh, look at that. It's like, no, actually, you actually need to understand what you're getting at here, and the conclusion you're drawing is wrong. You'd understand it more if you would have started from the bottom and worked your way up with your knowledge. But
exactly,
trying to work backwards and explain all this shit's a pain in the ass.
And it leads to confusion with them. Okay, so here we've solved it. dy. So if you see this dy dx, 2x squared plus 3x on the left-hand side, this is why you can do this problem in your head. And so when people say, well, how do you do calculus in your head? This is how you do it. Well, again, this is a very not all problems are like this.
All you need to do is a power rule. If you need to do the chain rule, you probably very few people can do the chain rule in their head. I'll say that. Very different, and we will get into the chain rule as well. I touched on it before, but I need to go more in depth in the chain rule, because when you start doing integrations and integration by substitution and all this other stuff, it's an integral part of all that. So
the reason we have the chain rule is, for example, this is a very simple function. It's the linear combination of two polynomials. The reason we need the chain rule is because we'll look at more complicated functions that involve composition of functions. So the chains refer to the compositions of the different functions. But go ahead. Steve, can I just make a major comment here?
Yeah.
So what we've done is Steve referenced that parabola y equals x squared. Now he's referencing another parabola y equals 2x squared plus 3x. And what Steve has done very neatly has given you a formula for the slope of any tangent line to the parabola at any point x. And namely, if you want to find the slope of the tangent line, you simply put in x. For example, if x is 2, the slope is 4 times 2, which is 8, plus 3 is 11.
Let me
Did I say that too quickly? Did everyone get that?
No, not all, but I just wanted well, I was going to put the slope in there, but
we should point this out, Drake. Steve is doing this out of the goodness of his heart. He's not getting views for this. He's not getting money for this.
Not by any means.
He's just simply doing this as a pure form of altruism. And, Steve takes a lot of maligning, most of it justified, but this is pure altruism.
Yeah.
I think, like I said, I'm very self-deprecating, but I do realize that, I do know a little bit more than people give me credit for.
Just a little, but yeah.
From the Clown Car Posse, at least, I think that the educated people in the GDC know that I'm not a moron, but I do have self-doubts. Of course, it's been a lot of years, but I do think to myself, I got the basics of this stuff down, and that's more than any of the CCP does. But anyways, this is what the graph actually looks like. So this is what that formula actually looks like. The 2x squared plus 3x will look like this, and you'll see that the apex goes down here, and here's where it crosses the origin. Here's the roots. Remember, the roots are where it crosses the x, right? And since we found out the derivative to be 4x plus 3, that's going to be the line that represents the derivative of that function. And as EO astutely points out, I could put in any value for x. I'll get a y value of where the slope is for a particular point on that graph and that function. So if I say, okay, at x equals 0, right? At x equals 0, well, what's 0 times 4? 0 plus 3.
Boom.
Here you go. This is what I'm at. This time, then so the time that's how you get this line, right? I mean, I could basically use this line to calculate any point by that formula. Okay, that's the time rate of change of that function. Does that kind of make sense?
Yeah.
Okay.
Good visual representation, actually.
Yeah, because the time rate of change at 0, right? This right here is going to be 3. Yeah. Okay. So let's see if I can move this over here, and let's see if I can actually show you why that actually works that way. Blah blah blah. Okay, finding the slope formula. Hopefully it doesn't get too tricky here, but bear with me here.
Oh, I remember these problems.
Yeah, these can be kind of these can get confusing really quickly. Not gonna lie.
There was something at the end that I kept forgetting to do, and I don't remember what it was, but it was something that you're supposed to. I'll remember it later.
All right, let's see if we can walk it through.
Steve, if I may, though, for beginners, where it gets confusing is all you need is the x value. The y value actually can distract you, so don't pay attention to it. All you need is the x value. That's
a good point. When we're doing this, you're going to find out we only really give a shit about the x value. Okay, that's completely true. So given the dy dx of x squared, we already know that's 2x, right? So we don't have to factor that anymore. You might have a problem that says, okay, find the derivative of x squared, then find the slope at p1, 1, right? That's how you're normally going to get some of these problems. It's going to ask you to find the derivative first of some function. But I'm going to assume that we already know the derivative of the function. Save us a lot of time. Okay, we already know the derivative of x squared. So let's find the slope at p1, 1. Okay, and if again, going back to our thing here, I want to know the derivative of this point, right? I want to know this black line. I want to know what the time rate of change is at p, and that's here. So what we're doing, okay, so I'm going to set f of x as x squared. We automatically know that, again, I'm changing notation. And I don't know what the rule on that is. Maybe EO can kind of guide me on that. I'm kind of changing from one notation to another. Is that kind of frowned upon? But I like it that way.
Completely allowed to that. Tomato, tomato. It's all the same. No problem.
Thank you. Okay. I just find it a lot easier. I like expressing dy dx this way, and I like showing the f prime this way. I just find it to be conceptually easier for me. Hey, whatever works for you, right?
And if I can just stand on my soapbox for a second, this is why so many people are drawn to mathematics, because some of the lively discussions you have in the great debate community never happen in math. Like nobody ever goes to war about different notations, and everyone understands what you mean. So it's great. Sorry.
Except when it comes to implicit multiplication by juxtaposition. There's still argument on that.
Oh, I'll take your word for it.
Well, some people argue that implicit multiplication by juxtaposition has a higher order of precedence, and in standard order operations it doesn't. So, but whatever. So the f prime of x we automatically know is 2x. Okay, we're just going to give you that. So I want to know at x equals 1, right? Was that point p? The slope of the tangent line is equal to the derivative at 1, right? Because again, what is the derivative? It's the tangent line at that point, right? So I want to know the slope of the tangent line at p, or if x equals 1. Same thing. These are all saying the exact same thing. So the derivative of the argument of 1, when I stick 1 into x when the formula is 2x, what do I get? What's the derivative? What's the slope of that tangent line at that point? You just put a 1 in there. So 1 times x is 2, right? So 2 is the slope of the tangent line at that point. Okay, so I now have the slope of the tangent line at 1. Does that make sense to you, Drag? I found out the slope. Here I've got the derivative of the function. I've given you that. You didn't have to figure that out. But I want to know what the time rate of change is at that point. So I just put 1 into x at point x or point 1.
Yeah.
Well, 1 times x or 2 is just 2. So the slope of the tangent line is 2. And what I'm showing you here again, let me get rid of this line. I'm just saying that this line here has a slope of 2. That's it. Okay.
Too easy. Oh, well, what was that? Okay, that was weird. All right.
You see that? You get that?
Yeah. No. Your screen kind of did something funny. Anyway, go ahead.
Okay. So I'm just kind of moving things around here so I can keep track of live chat. Me too.
We use the x variable.
Yeah, look at the link. The link to get in, I actually put in the G plus if you want to come in. Okay, so now that I have that, I want to know what the y is. The y1, right? The y1 is basically where we started from, right? It's just my initial function with x equals 1. Well, that's this formula, x squared. So I'm just sticking 1 into that. And of course, 1 squared is 1. So I'm just trying to find out this formula. I want to find out all the different argument or all the different terms in this particular formula is what I'm kind of looking for.
Are you going to derive the point slope formula now, Steve? Is that what you're doing?
No, well, yeah. I'm showing how to find the point slope formula for any particular function. But I know in here now, I know the slope, right? Let me rearrange this first. So let me rearrange this. This is my point slope formula. We've all seen this before. I'm just rearranging it. I'm just taking the denominator. I'm moving it over here, and I'm bringing this down. So that's all I'm doing. I'm just rearranging it. Now, when I start putting in numbers, right? I can put in the number for m. What's the m? M is the slope in the. Remember one of the first things we went over. This is why I want to go over linear equations first. Linear equations. The formula for that is mx plus b, right? Y equals mx plus b. Remember that? There's a reason why we went over this stuff first, because I mean, I think that a lot of stuff makes sense if you remember or start with the basics. So a linear equation is more simplistic than in a quadratic or a parabola. So this is one of the reasons why we went with linear equations. So the formula for y equals mx plus b, m is always the slope. But I know the slope now because the slope is the slope of the tangent line. So I can just stick in 2 there. Okay. I also know y1, right? And how do I calculate y1? Well, y1 is just 1 in the function of f of x. And I also know x1 because that's where I'm starting from 1, right?
Yep.
Right. So I could put all these different numbers in, right? And I'm just going to distribute these out. So 2 times x minus 2, y minus 1. Let me move this over here. And so I end up with y equals 2x plus 1 because I basically, there's 2 variables in here left, right? But I put in all the numbers I know. So given this particular function, x squared, all I need to do is find the derivative. I need to find this point at p 1, 1. Now remember, we only care about 1 here. We only care about the x. Y here makes no difference. So remember, that's kind of important. We only give a shit about the x. And the reason being is we only end up here with the x, right? We're looking for y, but we only end up with the x. We have 1 x unknown. But here's the formula, 2x plus 1. And if you look very carefully on this particular graph, look what happened here. At this point here, let me get rid of this tangent line. At this point, tangent line, I started with 1 line, which had a slope of 0. I had another tangent line that was getting closer, right? But when I actually reached that point, here was what the tangent line looked like. And I just created this tangent line by using this formula, which is 2x minus 1, which is we've determined is the formula for this parabola. And I can put in any value for x and get a y value out of it and tell you what the time rate of change is at that particular point. So if I put in 1 times 2 is 2 minus 1 is 1. So here's 1. Here's 1. So fx equals 1. Boom. What's y? Well, y is 2x minus 1. 1 times 2 is 2. 2 minus 1 is 1. Boom, here's my x. There's my point. That is why this formula works for this particular equation, or this particular x squared equation. So
yeah, there's a question in the chat.
That's where it gets a little more confusing. So I don't expect everybody to pick that up right away, but if you want to try to do this on your own, I give you your homework assignment, f of x squared.
Steve, can I talk to you Midnight?
Yeah, go ahead.
So Midnight, that's an example of a relation that
that's
easily solve this using implicit differentiation. But that's another hangout. If you want, we can talk off air. But basically, you can do this in 2 ways. You can split them into 2 functions, the top half and the bottom half, and just use the formula. It's much harder that way, but it's simple. You can still use the power rule. The exponent's 1/2. But there's a much easier way with implicit differentiation. I can see you doing that in the chat.
And that's where we'll be doing implicit differentiation too. Yeah, but we should point out at Midnight that a difference between a relationship and a function is a function always has a 1-to-1, but a relationship doesn't. Correlation. It doesn't.
For every member of the domain, there's a unique member of the range.
Yep.
A rule that assigns to every member of the domain a unique element in the range. Whereas for a circle, Midnight, please verify every x value except the ones that intercept the x-axis have two partners, two y values.
Because you have the top hemisphere over the y and the bottom hemisphere. But at y, when x equals 0, is that unique?
No, well, depends how big your circle is. For example, the circle of radius 1 will touch it -1 and 1, right?
Right,
and then
right.
Vertical tangent lines.
Yeah, so with the radius of 1, it's -1, 1, with y being 1, -1, 2, right?
Right, but the issue is -1 and 1 because we get vertical tangent lines there, which is a problem.
Okay, yeah, we will have another hangout. I may touch on it only because I'm not good at it, and I should be.
Oh, he's right. Midnight's right, but props to Midnight. He did it.
Yeah, no, I mean he's actually solving it as a differential equation almost. So, that's how you would do a relation, right? But I haven't got into relations because they're not the same as functions, and I haven't got into implicit differentiation yet.
You could have a lot of fun with this, and this would be in your wheelhouse. You could do these cardoids in these examples where we have to use implicit functions because it's just too damn hard to use it implicitly. And then you could have all sorts of fun. You could do cycloids, all sorts of neat physics stuff.
Cycloids are cool. Yeah, cycloids are really cool.
Sorry to derail.
No, I like cycloids because cycloids are, when you're tracing something for that path of the cycloid, it makes pretty cool stuff. But we should give Midnight Sparkle a simple differential equation, like a first order linear differential equation, like dy dx equals -y over x. How would you solve that, Midnight, using separation of variables and integration? Not as hard as you think, but that's probably one differential equation that most people could probably do in their head at some point. But we'll get into that another time. I think we're jumping way ahead, right? I don't know. Can you think of a simpler differential equation than that, EO? Because I think that's probably the simplest possible, isn't it?
Well, technically, the simplest differential equation is y prime equals 0. But
okay, that's trivial. But that's a trivial case, they call it.
Right. So the one they introduced Calc students to is y prime equals y, and as we did the other day, as we solved the other day, that's the solution is the exponential function.
Okay.
But hold on, you actually raised a good point, Steve. When we get into integral calculus, you'll see basically we are solving all sorts of differential equations. For example, if y prime equals 2x, what's y? You go backwards. And Dreg, let's bring Dreg into this. Do you have time to write that, Steve? Can you ask Dreg to solve that?
Yeah. Let's yeah, I was going to do I was going to show your prime thing, but yeah, let's see if I can do here. One sec. Go ahead. What am I writing?
Y prime equals 2x. Ask Dreg to solve that differential equation.
Y prime equals 2x.
Let me find a pen. Okay, is it y prime equals 2x?
Yeah. So I usually, it's been so long since I've solved different equations, but I always write them in this form.
But Dreg, let me help you. You just
this is wait. Let me see. I want to see if I can figure it out too. So this is a separable differential, right? You can actually say.
You guys are making way too complicated.
But this is how I work here. So 2x dx.
There's only one y variable.
Dy.
I just got dy over dx equals this 2x. So I mean, if I take what you call them both, I mean it's just dy out. Huh?
You have to integrate both sides.
Yeah, that's what I was saying. I was gonna I could take the derivative of y prime, and I just have dy over dx equals 2.
No, so integrations. So Dreg, now to solve differential equations,
I don't know the symbol for integrate here. I haven't worked it yet.
Look, I was just trying to make the point that what function, if y prime equals 2x, that means that the derivative of some function. What function was that? That's the question we're asking. Do you get that?
Oh, the integration would be reversed. So no, yeah, it would be like what? X. If you're doing it reverse, hold on, because it would be x to the second.
Yes, you did it.
Plus constant.
Yeah, because it would be x to the second.
There you go.
But you got to add that constant in, remember?
Plus k. What is it? Is it k?
C. Yeah, plus
you
k or
c.
c.
Yeah, so integrate 2 plus. So it's 2. So it's going to be x. Well, actually, I have to do the integration. X squared plus c, and I usually do them this way, and I know this is kind of annoying, but and I'll show you why I do it this way. So
Steve raised a good point, and when we get to that lecture, I've got a great feminist empowerment joke. Great joke. Ready when we get to there.
Because there are actually two different constants, right? Because each integration comes with a different constant. But because constants can be added together, you basically can just shove them together and put one constant together, right? So I end up with x squared equals c. Is that right?
X squared plus c. Close.
X squared plus c. You're right. I'm sorry. Yeah, x squared.
So there are other constants when you're doing it. What is a different type of integration?
The reason I'm doing it this way, and let me show you. And by the way, did I solve this differential equation correctly? It's been a while since I've done diffq. Is that right? EO?
Hi.
EO, I can't hear you. Okay. So yeah. So that's not bad. I haven't done diffq in a very long time. So, but here, what we're basically doing is we're basically
understand the.
Let me see if I can explain it, because it's been a while since I've done diffq. He gave us the initial thing, y prime equals 2x. What I did was, I don't like using prime notation for this. Again, this is just my personal thing when I did differentials. I like writing in a Leibniz notation. The reason being is you can actually see at this point that these variables are what's called separable. Okay? And when you separate the variables, all I'm doing is I'm taking 2x and I'm moving it to this side of the equation. And I'm taking dy and I'm moving it to this side. I'm separating the variables here, or Ronnie would say veritables.
Veritables.
So this way, the way I do this, I can actually see what's going on. Okay, now I am ending up with 2x with respect to x. Now, again, don't confuse notation here that you think dx are different, or it's like two variables of x in there. It's not. What this is basically saying is dx with respect to x. Okay, and I think a lot of people might get confused. Let me add a little padding in here so you can actually see that. Okay, because it's actually with respect to x. Don't think this is 2x times d times x. It doesn't work that way. Okay, so now I've separated the variables. Now I'm going to integrate both sides, and that's with this little sigma here. And you can actually this is called indefinite integration. You can actually put limits from the top to bottom, boundary conditions, I think they're called, right, of the indices. So I'm integrating 2x. Now what I'm doing now is I'm just doing the reverse of the power rule, right? So I'm taking the coefficient, I'm moving to the exponent, x squared, but I also am adding a constant to it, because when you do an integration, you're doing a general form. There's going to be a range of form. You're doing. Sorry,
Steve. You meant to write x squared plus c1 equals y plus c2, and then you can combine the x squared and into a single constant on the left-hand side. So you screwed up there with the.
You're right. I see exactly what I did wrong. It's y plus c2, and then I just put a padding here, but this is actually y.
Hogtie Champ, do you want to link in? Because Hogtie's in the outside chat. I know he likes math.
Drake, can I tell you why we need the constants, buddy? Can you imagine the y equals x squared parabola?
Y equals x squared. Yeah, it's a big not a hoop or a loop or like a U.
Now, can you imagine we can shift that up and down any way we want? The tangent lines are the same. Do you get that?
Right.
Because whatever I say, if I say x squared plus 2, right, I'm just moving that parabola. What happens to the derivative of a constant? It goes to 0, right? So this is a general solution set. This is saying that this x squared plus constant is a general solution because I don't know what my initial was. I could have x squared plus 5, and what's the derivative? 2x, right? What's the derivative of x squared plus any constant? 2x. Does that make sense?
Yeah, the derivative.
So this is giving me a general solution set. That's all it's doing. I know that's where a lot of people get confused, isn't it, you? Because they're not understanding that when you're doing an integration, you're giving a general formula that applies to a lot of different cases. Because I could take the derivative of x squared, I get 2x. If I take the derivative of x squared plus 5, I also get 2x. You don't know what your field, Steve.
Your field is physics, you know.
Well, it's really not, though. I wish you would. My physics was not field. I was trained to learn how to operate the power plant. I just had to learn physics and science in order to do that. But my training was specifically more in operations. Well, so I don't want people to think that I have a background in physics, because when I actually try to do a physics problem, I suck at it. I just understand concepts.
But the point I was trying to make is often with these differential equations applications, we get, field lines and isoclines, and we get different. And so it's really important to represent, entire fields with the equation. And then we choose a specific trajectory. Long story short, Drake, if you don't include the constant, your teacher will dock you.
Yeah.
Yeah,
I do remember that.
Yeah, because it's wrong. But I will tell you a story. A long time ago. We used to have in our work when I worked at Kohl's, we had this white, those big white memo papers that people use. They're like huge things, like for like charts, right? Just massive pieces of white folded, white graphing thing, and you write on it when you're doing a presentation, something like that. You know what I'm talking about?
Like an easel?
Yeah, like an easel. So there's this, it's like 3 feet across or 3 feet high, whatever. And we would, and one of the things that we would do is ask random questions on that thing, and just kind of a trivia type thing, right? Well, somebody who had a degree in mechanical engineering, so I'd be a wise ass, and he wrote, find the derivative to, it was like e to the x 3x plus 4 or something along those lines, right? Well, back then I kind of actually remember more than I did now, and I was like looking at it, and I literally solved it on the thing. And my manager, when my manager came in, the only manager that I didn't like, right? Well, because there was two, but one that I just couldn't stand. This was an idiot. And he comes in like, well, how'd you know how to do that? I'm like, Jesus Christ. I'm like, you really think I'm a dumbass, don't you? And but it was really cool because it was like a Goodwill Hunting moment, like, oh yeah, I think I know how to remember how to solve this kind of shit. And he was just like blown away. He's like, oh, I didn't know you knew any of that stuff. I'm like, well, you don't know anything about me because you're an idiot, and I don't want to talk to you.
I had moments like that when I worked for Lowe's a few months ago, because they were trying to figure out how to get a bag of chips to fall and knock down, because the vending machine gets shit in there gets stuck, right? And so I told them they were trying to figure out which thing to choose that will knock it down. I said, well, you would want to choose the thing higher up because it had more potential energy than anything closer to it. So you would want to choose the Cheetos up there, even though the one that you're looking at looks like it's a bit heavier. It wouldn't be able to push it with enough force because it has less potential energy from the fall. So ideally, you want to go with something higher up so it can have more potential energy that can actually hit it with enough force to knock it loose. And so you get two for the price of one.
Like gravity do the work for you, right?
Yeah. And so I sat there and explained it to people, just looked at me like I had a dick on my forehead. I was like, it's true. Like, I could show you mathematically why that's true. And so, yeah, it's just little funny stuff like that.
I got to tell you, I'm actually kind of thrilled with myself that I remember how to do a differential equation. So whatever. I wasn't expecting to do diffy-q yet. But anyways, let's continue on, because I really
go ahead and invite Hogtie. He'll be AFK. I think he said he wants to come in for a little bit.
Sure, let's get Hogtie in here. Why not? There you go, Hogtie. Hogtie should be giving these lectures. He knows calculus really well. Like I said, I'll sit through a lecture from Hogtie, or I'll sit through a lecture from Ronnie. I'd be down for either one. But okay, so let's actually show your picture here. So let me actually go to my thing here.
Oh, he did a great job on that expected value of that game. I caught that lecture. That was amazing. And I was shopping at a mall, and I really wanted to jump in that lecture. But yeah, that was amazing with the expected value. It was great.
What was it for? What game?
Drake, was Steve not there at that lecture? Do you remember that hangout?
Yeah, it was the one where you pay him $2 and then he flips a coin, and then I forget. Yeah, it's the same game that he told you about way back when, because the idea is that the trick overall is that if you play the game infinitely, you're always going to come out on top. Like I forgot what the ideal amount of, I don't know, if you bet an infinite amount of dollars, you'll come out on top.
Oh yeah. That's right. Yeah. Because and then I guess the solution to that is you should always play regardless of the amount.
Yeah.
Yeah.
I forget what the name of the game was.
That is called. Yeah,
there's a name for it, and I can't remember it for the life of me.
You have to come in and tell me. I honestly don't remember. I've heard it before even Hogtie mentioned it, but I didn't remember the details on it. But I did look back into it when he mentioned it. Like it's called this something. Freaking A. Yeah, I can't remember off the top of my head.
Are you going to jump into the power rule proof? See if I'm AFK.
Yeah. Let me see. I'm just trying to wait. My computer's being sluggish.
Is somebody leveling from level 1 to 110 and WoW without sleeping? Jeez. Okay, let me see if I can hop on my phone because I need to take a bath because I do have class tomorrow.
My computer's being really buggish here, so I got to get into where you put that picture.
Oh, in the Hangout?
Yeah, I mean, do you think we should bother or just kind of look at it real quick? Because there's a proof out there of why the power rule works based upon first principles, and you can actually plug and chug and do that proof. And EO has done a more elegant version of it. Here we go, where he used binomial notation, which is a much simpler way of doing it. But when you actually have to do this in college, you have to write the whole thing out. It was when I did it, so I can't find where you put this, EO. What
Can I see
yeah,
if you want, we can do it today, but do you want to just do this next time and then we can use it for any exponent, real exponent? It's up to you. If you're feeling up to it, we can go ahead.
No, let's finish it up. Let's just see. Let's just show them the picture real quick. I'm just remember where'd you put what IM did you pick the picture?
The chat. What do you call it, Dreg? Is it the external chat? The one.
Yeah, but which? Oh, here you go. I found it. A lot of external chats. Okay, so I found it. We're going to be showing it. 1 second here. Dun, dun, dun.
And what'll be fun is I did this in a couple of minutes, folks. So please check my arithmetic. I could be off on some of my arithmetic.
Yeah, I'm not going to bother checking this for you, to be honest. But I mean, the concept is legit because I was looking at the actual proof. This is very similar to the proof that I was going to use. The only difference is I didn't use a shorthand notation, and so you have to actually write this shit out, and it's just whatever. But basically, what he's saying here, I'm going to try to read through this. He's saying let n equals x to the n. See, n is an element of for any number for natural numbers, for the set of natural numbers.
Yep.
So n is okay. This notation here is called element. So he's saying that n is an element of natural numbers. So n is a natural number. Whenever you see that type of symbology, f of x, the limit goes to, this is the standard formula for what we just went over. He's putting in the x to the n here. So basically x to the n, and remember, we just put x plus h where n is here, right? So we end up with x plus h to the n minus x to the n over h. This is all easy so far, right? Now, when you expand all this stuff out, okay, now you're dealing with n though. Here's the problem that people may get into. X plus h squared, we know the binomial expansion for that because we've done that before, right? We just did it in the Hangout we just had. Everybody agree? But now he's using for any n of an element of natural numbers. So now it could be any n there is. And so now you have to account for that. That's where you use this binomial expansion, this huge, big old long thing, because this will work for any n. It'll collapse down to any n. Is that the best way to describe it, I guess, But you're using a shorthand. You're using a notation that I remember, but I don't remember. The n over 0,
so
the n over 1.
That's n choose 0. In other words, how many ways can I
n choose 0? That's what it is. N choose 0. Yeah, okay.
Combinatorial notation, not permutation.
I remember it as k n over k.
Yep. N choose k. Sorry, no, not over. N choose k.
N choose k. Yeah.
Combination.
You said it right in the middle here. Yeah, n choose k. So this is basically. Well, you know what you described. This whole choosing thing. I get. I've done it for permutations and combinations.
It's really simple, guys. How many ways can I choose in total? Well, once. How many ways can I choose? So let's take out our fingers. We have 5 fingers. How many ways can I choose one finger? That's 5. Choose 1, and the answer is 5. Everybody still with me? In general, the answer is n factorial over n minus r factorial divided by r factorial. Well, r is what you're choosing, or k if you like, whatever. In other words, it's the coefficients for all of the middle terms are the hard part, and that's what algebra students hate, and it's a convenient way of writing it out.
Okay, so the n plus n raised to the n, x raised to the n plus x raised to the n minus 1, all the way dot. So it's going to be n minus any value, which is we're going to call k. Okay, so this basically works for any value. This is forget the whole binomial theorem there for just a second. I mean, because again, that gets into a little more complex. You think it's simple, but this whole n choose k is confusing. I never liked it. So I'm not the one.
What did you guys do? Did you use factorials then?
No, yeah, we used factorials. Like it was like k over n plus k factorial, or something along those lines.
Right. To be fair, though, I had no idea you'd be presenting this. I just wrote this out for Dragon in a couple of minutes because I wanted to see it. But
we wrote it. We did things long way, you know, nasty hand. This whole way of writing it in this n choose k, I was familiar with, but I never was comfortable using it ever. So I'm not going to go there. But let's just move on. The binomial expansion collapses down. Basically, is all he's saying is just collapsing it all down. He starts canceling things out, and he ends up with basically the first term here, which is nx raised to the n minus 1, because everything else gets reduced to 0 as h goes to 0. That's basically what you're doing, right?
And just like all of Steve's examples, please note what Steve's pointing to there with his cursor is the only term that doesn't involve an h. So everything else is going to collapse except that first term, just like in all of Steve's proofs, by the way.
Yeah, that's a good point. Because every one of these terms has an h in it. It doesn't even matter. I think if you get the binomial expansion correct, they're all going to go away anyways. As long as you have the first term in there, it doesn't have an h value. It's not going to be affected, right?
Right, and that's the reason. Hold on, Drake. Can you see now? That's the reason the derivative of x to the n is n times x to the n minus 1, because everything else has an h term and collapses. Do you see that, buddy?
Yeah, because all he
I'm
did.
listening. I'm about to take a bath.
Okay, go take your bath. You know, display some water. Go do Archimedes' principle. But one thing I should note here that we kind of skipped, the way he was able to cancel out what h in the denominator is he factored out an h from every term in the top. And by factoring out an h in every term in the top, this left this term, nx raised to the negative 1, without an h, because this h got drawn out, this h got drawn out, all these h got drawn out or subtracted, right? So, I mean, if you have nx h squared, you'll then have nx h, right? So there's an h taken out from every one of these terms. But when you take an h out of this term, what happens? There's no more h. So that's why he was able to factor out this h, cancel it with the denominator, take the limit at h approaches 0. These all go away. Bam! You're left with nx raised to the nx minus 1. And so now we can use this now. So if I say x squared, what's the derivative of x squared using the power rule? Okay, well, n is equal to 2. That's you gotta remember that n is an element of all natural numbers, right? So 2 is a natural number. So 2 minus 1 is 1, and then you take 2 and you put it where the coefficient is here, and x, which is the coefficient. I end up with 2x raised to the first, which is 2x. So this is why that works. Now, it should be pointed out that because n is an element of natural numbers, you can't use the power rule for negative exponents, correct?
No, it gets, yeah, well. No,
there's some limitation there.
No,
I try.
No, Steve, it works for.
Does it work for negative?
Remember the derivative of 1 over x is minus 1 over x squared. Yeah.
Yeah.
It works for fractions
okay,
too.
wait. Okay. Does it work for 0?
Well, that's a trivial question because anything raised to the 0 power is 1.
Well,
right?
yeah,
So
right. But that's what I'm saying. The reason why we have to clarify n as a natural number is that because 0 is not considered a natural number in this particular instance.
No, honestly, the only reason we clarify natural numbers here is that exponents are a couple of chapters ahead. We're starting at basics. This proof works, and if you see the other attachment, we can use logarithms or implicit differentiation to prove this for any exponent, any real exponent.
Okay, I mean, I've always kind of wondered that when it comes to like real analysis that I could stop screen sharing. Why they choose, and you could probably answer this question help for me. Why do they choose n as an element of n, vice n as an element of z? Because we're dealing with integers or natural numbers, they're the same.
Starting with the basics, it's baby steps. That's the next thing to do. Remember, we take the derivative of square roots, we take the derivative of reciprocals, but we do that after polynomials because polynomials are the easiest critters. They're friendly. Historically, it's always been done that way in the math books because.
Wait a minute, but see, here's what I don't understand. But if n is an element of n, natural numbers are z plus, right? Natural numbers are the positive integers, correct?
They are, but this particular proof doesn't work for anything but the natural
numbers. Okay. I get it. Okay, totally get it now.
But
this particular proof, now you're saying n, you're only using n as an element of the natural numbers because
I had to use the binomial theorem. You saw that, right?
Binomial theorem. I get it. I totally get it now.
Yeah.
There
are versions of the binomial theorem for negative exponents, but they're a little more. complicated.
See, that would be, I would really like to have a hangout on that topic.
We have to use series and sequence and stuff. It's a lot more complicated, but yeah, we can do that if you'd like.
Well, I mean, like on like what are integers? What are rational numbers? What are irrational numbers? What are transcendental numbers?
Oh, I'd love to do that.
What's algebraic numbers?
You can't. By the way, you can't be transcendental without being irrational first. How's that for a line?
You can't be transcendental without being irrational first.
Chew on that.
All transcendental numbers are irrational.
That's right. So to become a transcendental, you first have to be irrational.
I didn't know. Why can't you just say okay, well,
there's a religious parallel there.
Yeah. Okay. Yeah, it doesn't work the other way around because obviously not all.
Right. And actually, can we make a parallel? People struggle with this. All Ferraris are cars, but not all cars are Ferraris. Ferraris are special cars.
Yeah.
Transcendentals are special irrationals.
Right. They're a subset of irrationals. And irrationals are a subset of the reals, and the reals are a subset of the complex, and the complex are a subset of the, I'm going to say, is it the hyperreals?
I just go up to complex numbers, but you get the point. People often confuse subsets, and it's all about logic. And I'm hoping, and I want to say this as diplomatically as I can, I'd like to teach people what contradictions mean, because what I've watched in the last several Hangouts, people seem really resistant to the idea of what a contradiction is.
Why don't you do a presentation on it then? See, I mean, you could easily, here's the thing. Anybody could do a presentation on stuff they know. You could easily do a math presentation. One of the things I like the great debate community like this is that I like to do presentations that I'm something I'm not an expert in, right? I like having lay people come in and present something and see if they can understand it and be able to explain it to other people. I find that to be great. And now it's great for an expert to come in too, don't get me wrong. But I got to tell you, a lot of experts in our community, when I listen to them, some of them might be like, yeah, this is explained really well. I get it. And other ones I'm like, I have no idea what the hell you just said. And it's not explained properly, right? And
well, if you have a second, let's just do a simple one.
Okay. There's
3 and not 3. Does everyone in the chat get that? So if I say that Steve has $3, if I then say he has $4, that's a contradiction. Now in real life, we can say it's an approximation, but here's the point. If I say, let's pick one at random, a certain king takes power at 22 years old, and then I tell you he takes power at 42 years old.
It's a contradiction.
True or not, there was such a king. But the point is 22 and 42 are different numbers. Therefore, it's a contradiction.
Yes.
And you can't finesse that. You can't finesse that. You can't resolve that. You could resolve it possibly, but the point is, from a purely logical point of view, it's a contradiction. And saying something to the contrary is just wrong.
Well, did you see how I wrote that down mathematically in that one post? Did you see my post on that?
I did, yeah, I did.
Well, I broke it down for G-Man, and I said, look, here, this is equal to this, equal to this. Here's the logic. What's wrong with it? Was my reasoning pretty good on that?
I did, and that was fine. And it's really contentious. I was just talking to Steve off air about this. Anyway, we should leave theology to another hangout. Sorry.
Yeah. Oh, yeah. So yeah, we're gonna be dropping out here soon, but yeah, if you guys got in the live chat, you guys got suggestions of things that we want to do hangouts on. I'm down for that. I don't mind relearning something or even learning something new to try to be able to explain it. Again, this is not for me being some professor or mathematician. This is just me showing that I understand this and able to explain it and enjoying it.
Is Kenny still in the chat?
I don't know.
Something that he mentioned in G-Man's hangout that we were all of what? It was something quantum, something retro causality.
Quantum. No, it's called quantum retro causality.
Okay, whatever the hell that is, we need to do a hangout on that because everyone was like, God. What in the hell is that?
Quantum, okay, it's a legit thing. Quantum retrocausality is how something in the present time can affect something in the past time. It's retroactive. It's retrocausational. However, there is such a thing that exists.
There's a famous Christian apologist called Richard Swinburne who's adopted that. So it isn't. Kenny's a bright guy, but it isn't new to Kenny. Several Christian apologists have already taken that tack. And Drake, do you know why they do it? It's a way of keeping Adam and Eve and death before the fall. Yeah.
And I get why they're doing it. I understand that argument. It's kind of a nuanced argument, but I understand that. But there is something to be said for retrocausation, right? When Richard Feynman did his lectures, one of the things he postulated was that during a pair production, you have a positron created and you have an electron created. They are the same particle, only opposite charge, right? But they're also temporally different. One is going forward in time and one is going backwards in time, but they annihilate each other so quickly that, if I'm not mistaken, you might be able to correct me, but I believe it's within a Planck's time, you can't even tell that that pair was ever there. There's no way to even know that a pair was produced. And these particles are constantly creating these pairs, constantly creating these pair reductions over and over and over again, just a infinite amount of time. One way the electrons going forward, one way the positons are going back, and they basically denied each other before they even came into being, kind of thing. There's a retrocausation that exists there.
Right, but let's be clear, and correct me if I'm wrong, Steve. This is an alternative to the Copenhagen interpretation. Let's be clear.
Yeah, yeah. I don't think it's compatible with the Copenhagen interpretation. Yeah.
No, in fact, it was created as an alternative because, as you know,
yeah.
we know the Schrodinger wave function works, but we can't explain why it works. And this is one way to try to help resolve that.
Lumet says it's wrong, and I'm not sure why he thinks it's wrong. The effect before the cause. Yeah, well, that's. But there is a way. The people have used quantum retrocausation to try to affect temporally things in the past. Now, I don't believe that's possible, right? But they have used that, Lamed. Sci-fi is one of the mechanisms by which they invoke in order to have temporal changes in the past. But you're right. The effect is before the cause on causal retrocausality. This is one of the things that they invoke in the quantum eraser experiment, right? Which I think is just completely misleading. Like quantum eraser loves quoting the quantum eraser experiment. It's a very, very complex experiment. I don't even grasp the experiment that much, but I don't think it has the implications that quantum erasers implying with it, but let's see here. You do the entanglement before you decide to measure. Well, that's for certain cases, but obviously with the retrocausality of the anti-pair creation, you're not digging any measurement. They're automatically entangled, but you're not entangling them, but you can. I mean, obviously we do things all the time like that. We entangle things, and then you see. What's that?
Isn't the standard experiment with the calcium ions split out 2 photons with opposite spin, I want to say?
I thought it was cesium.
It could be, but my understanding of the quantum eraser experiment is the following. With the spin at the beginning, and at the last second, you pull out the detector so that you get interference pattern. You get wave-like behavior instead of particle behavior.
Well, it's okay. Yeah, I was going to say it's cesium for the atomic clocks. Yeah, maybe you're right for the calcium for the quantum eraser experiment. Yeah, you change something, and you change it such that the light path wouldn't have time to go back and change its path because it's already decided to go one path, but it still it produces an interference pattern rather than not, or the other way around. But basically, you're changing something such that once the light has chosen a path, it shouldn't matter what you've done in the beginning part of the path, right?
Here's the point: if you try to detect it or observe it, you're going to get particular behavior. But if you don't observe or detect it, you're going to get constructive interference, right, or destructive interference, depending on what happens.
Constructive or destructive interference, yeah. It's a very if somebody wants to do an actual hangout or a lecture on the quantum eraser experiment, I'm down for that, because again, I know very, very little about it, just as much as what EO said. Basically, you're changing something conditional wise after the light has done something, and you're still getting.
Let's defer to Lamed, but my understanding of retrocausation is basically an alternative school to the Copenhagen interpretation. I thought so too.
So so is hidden variable. Oh, excuse me, the multi-world hypothesis. That's in contradiction to the Copenhagen.
The Bohm. You
don't Brogier de Bohm.
Yeah, de Broglie. So I just want to add at this point that anyway, this is far beyond me, Steve.
That's called pilot wave theory. Yeah, that's way beyond the scope. The pilot wave theory deals with how to get around the problem with hidden variables but you lose locality. It has to do with local realism. Again, we're way the hell out of the.
But wait, isn't it well established we lost locality anyway? Isn't that what Bell discovered in the 70s?
Well, what Bell's inequality is basically saying that you can never have a quantum mechanical system that satisfies the conditions where you that you can have both local and realism at the same time, I believe.
Right, Einstein believed in hidden variables. Didn't Bell show him wrong that basically those
Einstein did believe in hidden variables. Einstein wanted there to be hidden variables, but the Bell inequality says that hidden variables cannot exist, that you can never have a hidden variable model that satisfies all possible conditions, that explains all possible quantum states. Why are you making me go into this? I haven't looked at this stuff in ages.
It was brought up in the chat. I didn't.
You're sharpshooting me, aren't you? You see?
No, Drake.
No, I'm
brought
just
it up.
kidding.
Anyway,
No, I'm
I
just
have to
kidding.
go, Steve. Thank you so much.
No, thank you, EO. You know what? I'm just glad that I actually know a little bit about these topics. I'm so, you know, when they start talking about their biology stuff, guys, it's like I'm like, I love biology, but half the time I don't know what the hell they're talking about. I'm just riding along when they're going into their very in-depth stuff. So, you know, I like a lot of different subjects. I do read more than people think I do, but anyways, thanks for watching, guys. If you guys got any questions about these first principles, let me know, let EO know, let Drag know. And if you got something you want us to do, let me know. I'm going to be trying to do something on matrix theory coming up. But before we do matrix, I might do 1 or 2 other ones of just, you know, of interest, just something, because again, I wanted to kind of do this in steps. That's why I was like, let's do linear equations. Let's do order of operations. Let's do basic derivatives. I mean, let's get some of this out of the way before I start tackling some of the other stuff. Because as we learned, precept upon precept, and you can't just like jump in with by using, oh, let's just do the power rule and I know calculus. No, it doesn't work that way. But okay, so anyways, guys, I'm ending this. And Midnight Sparkle, thanks for listening. Lamed, thank you as always, and thank you for all the support you do for my channel. I might be putting, you had asked me before about putting up an Amazon wish list. I may put something up there, just something really inexpensive, but I don't know what I'm looking for. I'm looking for something that people have asked me to get where I can write on a tablet, just a little piece of shit thing that you write on it and it actually shows on the screen. So when I cross things out or I circle things or I can draw on it, it shows up. And I think they're called, I can't remember the name. They're not that much, but since you've asked me very kindly to put it on the wish list, no, you know, Lamed has been very supportive of my channel. He's like one of my big supporters, and I thank him very kindly from the bottom of my heart for all he's done. Again, my ass thanks him for him because my back hurts, and that's one of the reasons why I'm just probably not sounding coherent. Is my back really hurts, guys. But anyways, thanks for watching. And I'm out.